I'm going to try to, the subject here is the role of probabilistic analysis, but I'm going to introduce it because it's deep in my bones, it's what I do. I'm going to introduce it by describing the difference between the normal way plants are designed, analyzed, and operated, and probabilistic analysis. And this is so different from the normal way of thinking about things that I have to introduce it by describing the traditional way. I want you to imagine that the plant that's out there, it's out there, right? It's that way. That the plant that's out there was, as it was, designed and constructed using the traditional engineering methods that have been with us forever. And that's the case. The way the plant was designed was to make sure that all the functions that are needed in normal operation can be accomplished, like flows of water and heat removal and valves that function and pumps that pump and electrical things that provide power. And all those things were designed into this plant using traditional engineering design methods of the kind that you wouldn't think were very, and really are not very different than if you were designing an oil-fired electrical station, or if you were designing a refinery, or if you were designing a smelter. That is, you do a design, and then you postulate various upset conditions, and then when you're ready to take this conceptual design and make it specific, the way you do the design in detail, if you're a designer, at it might be PG&E, or it could be, for example, their contractor Bechtel, was you have a specific pump that's supposed to pump a certain number of gallons per minute of water at a certain temperature in certain conditions. The design of that pump is accomplished following an industry standard that has been adopted and used everywhere in the world for things like that. In this particular case, it would be an ASME, an American Society of Mechanical Engineers code that tells you how to design pumps. By the way, there's a code for telling you how to design elevators. There's another code that tells you how to design this thing. There are codes for almost everything, and they're industry codes. If you're pouring concrete at a nuclear power plant, there's a code from the ASC, from the American Concrete Institute, that tells you how to pour that concrete. Those codes were there before the nuclear industry, and when the nuclear industry came along, they adopted the same codes, but in almost every case, they made those codes more rigorous. They had more care, more margin, more quality assurance, more documentation to make sure that things were going to come out with better quality or better assurance of quality than if they were just pouring a concrete pad for, let's say, the parking lot out here. And so when you've got this design and you've got to design individual specific items, each individual specific item is designed to an industry code. If it's a building, it's designed to an ASCE, American Society of Civil Engineers code. If it's a heat exchanger, it's designed to an ASME code. If it's an electrical bus, it's designed to a code from the Institute of Electronic Engineers. The IEEE has codes for carrying electricity. By the way, it's the same code that IEEE has codes for electricity like this, and they also have codes for nuclear power plants. And they're different, but they're designed for a particular function. And the nuclear industry, in the old days, the Atomic Energy Commission, and now the Nuclear Regulatory Commission, has used those codes and adopted them as the fundamental way every single item in the nuclear plant is designed. Nothing out there is designed except using one or another industry code. And the codes also call for and have requirements for maintenance. So if you have a pump, you've got to maintain it to the maintenance requirements in that ASME code. And if you don't meet the code. The NRC in almost every area has adopted those codes by reference, and it's what they use and what they inspect against. And that's fine, and in fact, as far as it goes, it's a wonderful system because you need designers at places that are designing things to have specific rules about what they design to and why. And those things then, when they've been designed, are intended to accomplish a particular function. So for example, a concrete pad has to be able to withstand a certain amount of weight under certain conditions, temperature and so on. A wall has to be able to hold things up that are attached to it or things above it. That's civil engineering. An electrical bus has to be able to carry a certain amount of voltage in amps and withstand transients, electrical transients, and still perform its electrical function. And all of those are embedded in these codes. And that's the way we design these things. Once you've decided on how much, and there's another design process, figuring out how much flow you need, how much electricity you need, how much water you need, how much steam there is, and all that stuff. And the way the nuclear industry evolved, everything follows those codes with a superstructure of a different kind. I'm going to explain the superstructure, okay? The superstructure is that, and this was in the very beginning, the Atomic Energy Commission, now the NRC, and with working with the industry together, thinking this through, they came up with, at first, about 6 or 8, and we now have about 15, what are called design basis accidents. They're different kinds. A design basis accident is a particular accident for which this thing must be designed and with very high assurance shown to perform. And I'll give you the example. One design basis accident is you stipulate that the largest pipe in the pressurized system out at Diablo Canyon suddenly just breaks. We call it a double-ended guillotine break. It's as if the pipe just disappeared and all the pressure flows out that thing. That's called a large break loss of coolant accident. You don't ask how it came about. You just stipulate that it happened. That's the initiating event. The reactor must be designed so that it can keep the core cool when one of those things happens. That's one of the superstructure accidents. So when everything else is done, you have to show that too, and there are about a dozen of them. For example, one of them stipulates that you need to shut the reactor down, but for some reason, not stipulated, the control rods don't go in. So it's called a transient without scram. In other words, a transient in which you can't put the control rods in, and therefore you can't shut down the chain reaction the normal way. The reactor must be designed with other systems and other functions to safely keep the core cool and radioactivity contained in the event of one of those. That's another one of the stylized accidents. Yet again, another one is a total loss of power. You don't stipulate how it happened, you just stipulate that it did happen, and you have to show that when you have something like that, the reactor will shut down with other equipment that is designed into the plant. And that's the basic way in which these plants are designed, and that's the way they're regulated. The regulations require that the codes and standards and the rules that the NRC wrote about these accidents are all followed, and if you meet all of those, you get your license. Okay? Now, when that was done, back in the 60s and 70s, and the rules were being put together, the typical industry expert at the time would have told you that having been so, large accidents with large releases were very, very incredible. That was what everybody said. They didn't know how incredible they were, but they used words like incredible. Okay? And it wasn't until 1973-74 that a methodology was developed to work out whether or not that was so. And we now know it isn't so. That's called probabilistic analysis. I'm going to talk about that next. We now know that the word incredible is baloney, that in fact they're credible, they have understandable frequencies, they're low, but they're not zero, and those frequencies are what are worked out by a probabilistic analysis. Now I just have to, before I put up the slide, I'm going to just have to explain. So the way this was done was all this stuff was designed with this, using all the industry codes that have been in existence, although the nuclear ones have more rigor and certain more margin. And then the AEC and the industry together put together, originally it was a few, but now they have about 15 of these design basis accidents, like the one I said where you can't scram the reactor, it still has to be okay, or the large break LOCA, and then you still have to be able to cool the core. And you have to show that that's so, okay? Using other equipment. But now let's come to the rub. Using other equipment. There is nothing on the planet that works perfectly. Therefore, it's easy to say to yourself, what if the other equipment isn't 100% effective? Something doesn't work. Okay? That's the accident we fear, because we know that if everything works according to the design, it's going to be okay. The thing that isn't okay is, well, you couldn't scram the reactor, so you call in this other equipment, and there's a small probability the other equipment isn't going to work. We think it's going to work, we have high confidence it's going to work, but it's not perfect. So the breakthrough of 1973, and the person that did it was named Norm Rasmussen at MIT, and his colleague Saul Levine in the nuclear regulatory at the AEC staff at the time, NRC staff. These two men, Levine and Rasmussen, working with a team of people, developed and applied a methodology called PRA, Probabilistic Risk Analysis, which I'm going to describe to you next, which enabled them to work out the probability that nevertheless, even though you did this, one of these accidents would actually evolve into a disaster, a core melt accident with release. Because although there was very high confidence it was so, it sure isn't incredible. And the key to that is a different way of thinking, and I'm going to talk to you about that in a minute, and then you'll understand. The key is that once you've got this thing all designed, you've got to analyze accident sequences that, despite all of your efforts, lead to this core melt accident you don't want, which is undesirable, and then the release later, which is undesirable. Those things are not incredible. They, in fact, have understandable probabilities and understandable consequences, and an analysis was developed in 1973, 74, 75, it's called PRA, that demonstrated that, in fact, this was so. And the key is identifying accident sequences that go all the way to the end of the disaster. Now put up the next slide, the only slide, I only have one slide, I'm going to describe this to you, okay? Here's what the key was. Until 1974 with Rasmussen and Levine, the engineering community thought it was in fact not possible to identify all of the accident sequences that might happen. They thought there were too many, they thought they were too complicated, and they thought it was undoable. But this team, there were about 25 of them, they produced a report called the Reactor Safety Study, or Report WASH 1400, this first PRA. They proved to the world that they could identify all the important accident sequences. It turns out, depending on how you count them, because some are similar, there are 200 or 300 or 400 of them. You know, if you can, some of them are similar, so some people think there's only 40 of them, but there's really 200 or 300 or 400 of them. And each accident sequence is defined by something that happens, and in the end, you get a release of radioactivity from the core. It may not go out of the environment, but it's a release from the core. It's a really bad accident, okay? Now let me describe. An accident sequence is defined in my approach by the following. There's an initiating event. It says right up there, it's an initiating event. You know, a valve fails, a pump jams, a human makes an error in the control room, or an earthquake causes a wall to fall that knocks over a heat exchanger. I mean, you know, you can imagine any number of initiating events. But there is an initiating event. If it's an earthquake, it might cause several initiating events at the same. The earthquake can cause 3 or 4 things to fail, not just one. Whereas if it's just a heat exchanger jamming, that's one item, okay? But there's an initiating event which starts a sequence of events, and the reactor, remember, is designed so if you have a pump that jams, there's another pump that's supposed to be there to pick up the load or to perform the function or there's a valve that's supposed to close. So you have to think through an accident sequence in which, even though that's designed to work, it fails too. And then, okay, if it fails too, what next? Well, there's something else. It fails too. Almost all the accident sequences in the original report or in the PRAs that we look at have 3, 4, or 5 failures, not 1 or 2. There are very few with only 1 or 2 failures. In fact, I can't even think of one with 1 or 2. But even though they're 3, 4, or 5, they can happen, and the key was 2 things: to identify the sequences. It's a pump, then it's a valve, then it's a human error, then something. And by the way, a lot of them are human errors. In other words, you know, 2 things fail, and the human in the control room's got to do something. The probability that he gets it right isn't 100%, it's only 99%. 1 time in 100 doesn't get it right. And we have data about that, by the way. We have data on human errors, actually real data from things that are collected in the real plants, that are running today, and we collect those data. And so you work out this sequence in which you have the initiating event, and then the probability the pump that's supposed to be there to work anyway is only 99%, there's a 1% chance it fails, and then the human makes another error, maybe that's another 1%, and so you work these out, and you end up with an accident sequence that has an initiating event, 2 or 3 or 4 subsequent errors. Some of them are failures of equipment, and some of them are human errors. I mean, there are all these different sequences. There are a few hundred of them. And you end up with a sequence that leads to the undesired core damage accident. And each sequence is characterized by 3 things. It's characterized by a sequence of events. It's characterized by a probability of occurring. And it's characterized by a consequence at the end. Okay? It's very important. Think about that. The probability occurring, there's a frequency per year of the initiating event. It might be something that, by the way, some of the initiating events happen every year, and some of them only happen every 1,000 years, and it's very rare, but nevertheless, there's a frequency of the initiating event, and then there's the probability that the next thing didn't work, or the human made the error. And you work that out together, the sequence of events, and the thing that characterizes an accident sequence and characterizes the different accident sequences, they all have different probabilities of occurring in a given year. Some of them are 10 to the minus 4 per year, which means every 10,000 years, but they add up. Some of them are 10 to the minus 6 per year, and they're characterized by an initiating event with a frequency, and then these other consequent failures, which may or may not happen, and they usually don't, but they have different probabilities. So, as I said, what characterizes an accident sequence is an initiating event, 1 or more subsequent events. I'm now looking at the slide, usually equipment failures or human errors. And then in the end, you have a sequence, and it is characterized itself by a frequency of occurrence. Typically, by the way, the sequences we deal with are about 10 to the minus 5 per year. That's 1 every 100,000, but there are a lot of them. And then there's some undesired endpoint. The sequence ends. Maybe it ends with the loss of coolant needed to cool the reactor core. Maybe it ends with a damage to the core, or it might even end with a big release. A small release or a big release. Now, the breakthrough was that Rasmussen and Levine and their team demonstrated that it was possible to identify all of the important ones. And although at first when they did it, people said you couldn't have got them all, 10 or 15 years of hard work by everybody else actually demonstrated they did find them all. It was remarkable. They did a wonderful job. We haven't discovered any new ones in the last 25 years. By the way, the Rasmussen's report's going to be 40 years old this year, and it's really a remarkable thing that they haven't discovered any important new ones since that time. And at first, we didn't have enough data about the subsequent failures, but now we've gathered a whole lot of data about everything. There's hardly any of these subsequent failures that we don't know what the probability is. Sometimes it's 1 in 50 that it won't work, and sometimes it's 1 in 500. So that's all been gathered, and we have the data, and these analyses are now robust. Okay? Now, let me describe the initial reaction and the subsequent reaction, because it's very important that you understand. When Rasmussen and Levine published WASH 1400 in 1975, the nuclear industry's reaction was the report can't possibly be right because we've been told and we believe that the probability of these accidents is way, way lower than what they found. What they found was the probability altogether of a core damage accident was a few times 10 minus 5 per year, which if you ran a reactor for 100,000 years, you'd have 2 or 3 of them. Okay? A few times 10 minus 5 per year is what they found. The nuclear industry said, that's way higher than we thought. The people that were against reactors from the start said it couldn't be right on a different grounds. They showed that very, very few of the accidents leading to core damage produced a release. Most of them didn't. And the people that didn't like reactors said, they can't possibly be right. We've been told that every time you get a core damage accident, it contaminates the state of Pennsylvania. You remember that in 1970? And that turns out not to be true. 3 Mile Island didn't contaminate the state of Pennsylvania. We believe, most core damage accidents don't actually produce a release, and most of the releases are small. There are big ones, of course, but most of them aren't. What we've learned is that most of the core damage accidents, as bad as they are, don't produce releases because of different equipment configurations, and we've done this analysis so many times and we understand it, that the probability of a large release, once you've had the core damage accident, is only a few percent. That is, if you imagine we ran this experiment for a long, long time and we had hundreds of these things, only a few percent of them would produce a release, like what happened at Fukushima. Most of them don't, because the equipment is, and the containment is, and the chemistry is, such as it is, that most of them are more like 3 Mile Island. And so both sides in that debate in the 70s thought the report couldn't possibly be right. One side says the consequences can't possibly be that small most of the time, and the other one said the probability is way too big. But now, in the intervening decades, everybody understands that this is so. That most core damage accidents, although they're around 10 minus 5 per year, actually don't produce a release, but the probability is around 10 minus 5 per year, and for some of the reactors, it's around 10 minus 4 per year. And if you don't mind my saying, when I first went to the eastern countries in the Soviet bloc after the Soviet Union collapsed, I was one of the people that went there at first, and we studied their reactors. I'm talking about the reactors in Russia and in the Ukraine and in Bulgaria and in Hungary and the Czech Republic and Armenian places. Some of them had core damage frequencies as we worked them out at first that were 10 minus 3 per year, a factor of 100 higher than ours, and we were aghast. And they've been fixed so they're not as bad. Okay, so now let me come to what we've learned. We do probabilistic analysis, and the main thing that probabilistic analysis does is it concentrates on realistic accident sequences. An actual accident sequence, there are a few hundred of them. Each one is studied, and the industry has worked very hard to intervene where they can in each of those accident sequences to say, oh golly, the real problem with that accident sequence is that feed water pump isn't reliable enough, and they've worked to make them more reliable, and they've driven the numbers down. In the intervening years, the core damage frequency of the fleet of American reactors has been driven down about a factor of 10 compared to what it was then. That is, the probability of an accident, we believe, is about only 1/10 of what it was then. It was around 10 to the minus 4 or so. We think it's lower than about 10 minus 5 for the whole fleet now because of these things that have happened. And the most important things have been reliability of equipment and improvements in the humans. I'll talk about the control room thing in a minute. Human error was so important in those days that humans were making errors in the control room all the time. We see way fewer human errors now than we did before. Way better than a factor of 10. How'd that come about? It's easy to explain. Every plant has a simulator and they're training on it 400 hours a year. They used to have just one simulator at GE in Schenectady and one simulator at Westinghouse in Pittsburgh, and they trained on it 2 weeks a year, and it wasn't really their plant. And they were making errors all the time. And now those errors are fewer, and they're of fewer consequence, and continuing to try to drive them down. And the human errors are way lower, and we know that. The equipment's way more reliable, and we know that. And altogether, these sequences taken together are way less probable than they were before. Now, let me try to understand for you what this means. What this means is that because of this analysis, we now think about all sorts of things in the plant safety in a different way. Before, the emphasis was on making sure that each piece of equipment met its code design and its maintenance design. If you did that, you were safe. And the regulations still only call for that, by the way. That's what they call for. If you do that, you get your license. If you keep doing it, you keep your license. But we now know that's not sufficient. We now know that equipment designed to those codes and so on produces the reactors that were the reactors of the 70s and 80s. But Diablo isn't like that now, nor are the other plants. They're better. Why are they better? Because over and above the codes, which you got to meet and which they do meet, the industry as a whole has imposed more rigorous maintenance, more rigorous analysis, and more rigorous human training, so that the number and importance of the sort of things that go on in these accident sequences is far less frequent. It's not perfect, by the way, and I'm not happy with it, but it's way better than it was. And that's because the industry, while it meets the codes and gets its license, the reactors are way safer. Now, there's an important thing I want to say. A reactor that meets all the regulations could still run today with those poorer performances from the 70s, because almost none of those things have been changed. There are a few things that are changed. But no one would let a reactor like that run in this country today. Those reactors would be landed on by everybody in the industry, quite separate from just us, because they wouldn't be safe enough, even though they could meet their license, and they do. So what I'm trying to describe to you is, because of this advent of probabilistic analysis and the emphasis on accident sequences and concentrating on the accident sequences and seeing what they are, and seeing that the main thing in that accident sequence is that human error. The main thing in that accident sequence is it's that feed water pump. So we're going to work like the dickens to make it better beyond the codes, beyond the industry codes, most of which haven't been upgraded very much. And what that means is two things. Not only are things better, but there's a crucial insight from the following, and I want to try to explain it. This is the last thing I'm going to say, I think, which is that an accident sequence of the kind I'm describing might have 4 or 5 different things. From time to time in this industry, we have 1 or 2 or 3 of them happen, and then it ends successfully. I'll call that a precursor to a big accident that never got to the end because it stopped successfully, because this failed, and this failed, and then somebody did something right. And the end meant there was more. We've studied those precursors to death. Everybody studies them. When one of those things happens somewhere, here or elsewhere, the whole industry concentrates on figuring out what it was, and they train operators and they train maintenance people so as to reduce the probability that that thing might happen somewhere else. And that emphasis on understanding that operating experience is a part of what has made us concentrate on the important stuff and not the less important stuff. Now, we need the strict rules of regulation as the minimum, and we've got them, and if you do those, you get your NRC license, and if you keep doing them, you keep it. But I want to insist that that NRC license today, and everybody in this industry knows that, is not enough. That minimum is not an adequately safe reactor. Nobody in the management and in the operations of PG&E thinks that either. Nobody in any of our plants thinks that. It's been a 3-decade process of inculcating and convincing people that meeting the regulations is not only not sufficient, but that those regulations, as important as they are merely the start of trying to get more reliable and better human performance out of these machines than would have been the case if you just met the regulations. How do we know that? Probabilistic analysis. So that when we have something goes wrong, we said, what accident sequence is that? Oh, it's number 11. Oh, didn't that happen in Spain 3 years ago? No, that was different. And that goes on worldwide. It's really quite a remarkable thing. Now, there's another thing, too. When a deviation occurs, this sort of analysis helps everybody in the group that studies this stuff, like me, to understand whether it's a huge or only a modest issue. Because a lot of little stuff isn't so important, and a few things are really important. And it helps you prioritize where you want to put your effort. Because most little things that are reported aren't of importance, but we're glad we're reporting them, as you never know, and so you got to report them all, and you got to look at the ones that are. And so there's been, on two sides, the regulation side and the operation side, have both been concentrating their efforts on using PRA insights to help them regulate. The inspectors at the plant have a new process, it's about 10 years old now, in which they use these insights to help them prioritize where they inspect carefully and where they don't have to inspect so much and it doesn't matter much. Okay? That's really important for you to understand. On the other hand, on the plant side, the maintenance and operations people also use these methods to say, Here's where there was a problem somewhere else. We've got to concentrate, and here's where it's not so important to, what we're doing is already enough. Okay? So that's the end of that discussion, but I want to jump to the second topic just because, and it's the same topic, but I just want to jump to it. It's not on this slide. It has to do with the importance of the control room and the operators. And I'm going to start with an experience from not this industry, but from the aircraft industry. It's really important to think about aircraft as an analogy. As you know, and if you don't know, I'm about to tell you, but I hope you know, when you get on a plane to fly from here to New York, or from, by the way, tomorrow I'm going to fly from here to Oakland, the probability of not getting there safely, of a crash that kills me, is about a factor of 30 or 50 lower than it was when I was a young man. Okay? We just don't have accidents very commonly. We have these large ones that kill a whole bunch of people once or twice a year, and we used to have even more of them, and there was only one tenth or 1/30 as many flights. Now, you understand that, and I do too, and I'm grateful for it. But if you look at the big accidents in the last 10 years that have, commercial crashes, most of them are human error. Very few of them are equipment failures. Okay? You got to think about that. Almost all of them, there's an exception or two, the initiating event was a human error, and then what caused it was a human error. Some collection of human errors, rather than some equipment that failed in flight, or failed to take off, or failed in landing. When I was a young man, way more than half of the crashes were due to equipment failures. They've gotten rid of them, to their credit. Good for them. It almost never happens. Landing gear just don't fail. Engines just don't fail very much. Control systems don't fail much. It's human error. Thank God for what they've done, and in the airline industry, they're concentrating on human error. That's a big deal. Well, that's true in the nuclear industry as well. You need to understand, if you look at the accident sequences that bother us today, the most important accident sequences are accident sequences in which we can write down and can be concerned about some combination of human errors that get you in trouble. And the major push in the last 10 years, and it's been successful, has been working on the human error side. It's not just human errors in the operators, human errors in maintenance. The maintenance person does it all right and then doesn't restore it. The maintenance person is working on train A when he should have been working on train B. We don't have much of that, but they used to have more of it. And so the remaining big concern that Bob Budnitz has is that what's left is, like aircraft, is trying to figure out how to reduce those human errors even more. And that's where the control room and training comes in. I just want to leave this almost my last thing. Today, the simulator training that they get out there, it's 400 hours a year. Every fifth week, they're in the simulator training on oddball things, is the key and has been the key to reducing still further those human errors. Things like three-way communication. Things like, I'll just give you the example. It is a classic. If you heard me say this before, I'm going to say it again for you. It was just 2 days ago. My wife says to me, I'm cooking a chicken. It's supposed to be 375, but it might have been 350. Will you go check? Right? Degrees, right, in the oven. I went in the kitchen, it was 375, I said, it's fine. Okay? Not in a nuclear plant. In a nuclear plant, I would have said, it's 375. And she would respond, yes, I heard you, it's 375. All right? In a nuclear plant, if she said to me, move the temperature from 350 to 375, I would say to her, you mean you want me to move the temperature from 350 to 375? And she said, yes, before I did it. And then after I did it, I said, I moved it from 350 to 375, and the other person says, yes. So this sounds clumsy, right? But we've seen it in the control room. The human errors from that sort of thing have been dropping dramatically industry-wide, dropping, where they almost none of them. It's great. Isn't that wonderful? It's not perfect, but it's much better. And things like that have become the last bastion of things to do to make sure that we keep those things low probability. You can't eliminate them, but they're much lower probability. So the second part of this thing I wanted to say was that the role of the control room and the operators and the simulators is, I think, the last frontier of dropping these things, these accident sequences, to less frequency and less importance than they used to be. So now I'll leave you with just one other thought, and it's a really important thought. You might say, well, why do we have operators at all? Why don't we just automate everything? Okay? Well, there's a good deal of that's going on, but the designs we're running now, like out there, you can't. Nobody I know believes you can automate those things without humans. We just don't believe that. It's not sensible. We have designs thinking about in the future. Per Peterson, in fact, at Berkeley, he's not here, but he's working on one, where the amount of human intervention is way less important and way less common because most of it's automated. But that's not this one. None of us know any way to run these large reactors that are out there, the ones we're running now, without human intervention. We just don't know how. It would be insane. Therefore, we need the humans. Therefore, we have the susceptibility. Therefore, we have to work on the susceptibility to drive it down, but we can't make it perfect. And it's never going to be perfect, and we're always going to have this probability. And it's probably, we're going to reach a stage that's pretty irreducible. There's going to be a certain level at which we can't reduce it any further. And then each person has to decide, and the NRC has to decide whether that's low enough that it's acceptable. Because, it's not zero. And there are three different arenas. The operators, the maintenance people, and the engineers. Because so much of what goes on in those plants involves the third one, the engineers. Engineers are the ones who, when there's some new thing comes along, have to think through how to do it right, or how to make it better, or how to improve it, or how to eliminate. And engineers they're not error-free either. The analysis may not be error-free, or the analysis may be based on data, which themselves are not error-free or mistaken. So when it comes to the human side, it's the operators and the maintenance people and the engineers, all of whom have this susceptibility, all of whom contribute to this remaining risk, and all of whom we have to work on hard. And the way I see the challenge of reactor safety for these machines in the next few years, or the next 10 or 20, is working real hard on all three of those things. And I believe that the whole industry is on board on this, and that everybody's working on the same work together, and that major progress is underway. But is it perfect? No. Is the probability zero? No. What is the probability? We kind of think it's around 10^5 per year or a little better. Now I'm going to do a little arithmetic for you. There are 400 reactors running in the world. If you believe it, 10^5 means that you're going to have an accident every few hundred years with that fleet. Or it's a percent or so every few years. Okay? And I actually believe that number's right. Then you say, well, how in the world did Fukushima happen? And that's easy. They totally violated the most fundamental idea of all, which is they didn't even design for a big thing that they should have known was going to come along way more often than they thought. And the whole industry I'm in, every one of us, our mind is blown by how that could have happened. I mean, it just really disturbs me deeply. They should have known. Of course, they should have. What's the probability that something like that will escape us here? Well, it sure isn't zero, I can tell you. It's not zero. We hope it's small. We think it's small, but it's not zero. So let me go back just to reiterate. The key, I think, to understanding reactor safety today is to concentrate on accident sequences one by one and make sure we understand each one, understand what contributes to it, and find those things that go wrong and work on reducing them. We'll never make them zero, we've got to work on reducing them. Okay? number one. And number two, we have to constantly be on the lookout for something new that we haven't analyzed. Okay? Because that's outside of the thing I just said. Something new that we haven't analyzed. Like the Japanese didn't analyze the tsunami. It's terrible. Who would have thought? And that taken together is what I think is the major challenge to nuclear safety in the community I'm in the next period, today, in the next few years, and for a long time. And in the end, the question about whether they're acceptable is a different question. It's completely different whether they're acceptable. You and you and you and you and you each have to decide whether 10 minus 5 per year is acceptable. Some people think it is, some people think it isn't, okay? But, and I'm not going to go there, I'm going to tell you that I think those numbers are about right for our plants. Unless there's something really missing like the tsunamis at Fukushima. We don't think there is here. But nothing's perfect, okay? I'd be happy to entertain any questions, and also about what Per said. But if you want to know what I think is the role of the Independent Safety Committee, it pretty much goes to what the things I just said, but then you get down to the details, right? There's a whole lot of detail. Systems, humans, maintenance, engineering, external, you can list them. All the things on our open item list, all the things we look at. They are all concentrating on that, one after the other, okay? Questions? Go ahead, Sherry. You got to put it on. Got to push the button. Sure.
Sherry Lewis, Mothers for Peace. That was impressive. I enjoyed it. A couple of things: you did not deal with the radioactive waste.
Oh, yeah, no. Excuse me. I was talking about the safety of the reactors, of course. I wasn't dealing with that at all. I mean, it's just completely off the, right.
Well, the other thing...
No, I mean, I completely understand, but I was talking about the...
Okay, I'll confine it to that.
I've spent my life trying to figure out how we can make sure we don't have any core damage accidents.
I'll confine it to that. I like what you were saying.
I mean, completely, of course.
Right. I like what you were saying, but not everybody does that. You were talking about, I imagine, you're pushing to have this attitude of BRA throughout the United States, and I know you do go to another couple of countries and talk to them, but there are places elsewhere, this is not Diablo then, there are places elsewhere that don't deal.
Well, actually, not in the U.S. anymore. Every plant...
No, outside the United States.
I agree with that. No, for sure. Although I can tell you that I'm going to Armenia next week, they didn't have a PRA group, and now they have a PRA group of 10 people, and with some help, they've actually done a PRA in their plant, and they're using all this stuff, and the plant's better for it. And this is in in Yerevan, Armenia, halfway around the world, okay? So things are better.
Simone Malba from Los Osos. So where does the unpredictability of Mother Earth and climate fit into this formula?
Absolutely. Well, I don't know about climate. It doesn't affect these plants in the short term. But the principal unpredictability has to do with the large external events like tornadoes, hurricanes, earthquakes, and the like. Okay?
I was thinking about it in terms of weather, like unpredictable, like flooding, we'll say. El Nino comes down.
Flooding's another one. I mean, that's on that list. That's right.
Okay.
Yeah, you bet. All of the plants have done a new flooding analysis after Fukushima, including Diablo, and they submitted it last year. At Diablo, the two issues were tsunamis and a great big rains like the Dickens. We call it local intense precipitation, right? But if you're on the Mississippi River, of course, you know what that one is. And if you're on the Atlantic coast, it's storm surge or hurricanes. Every plant has done an analysis, a new probabilistic-based, although it's not fully probabilistic analysis of the flooding stuff. And the NRC is reviewing them now. And I'm actually an NRC contractor doing some of that review, but not at Diablo. I've recused my, at other plants. And to my surprise, about 10 or so of our sites have found that their flooding protection wasn't as adequate as they thought, and they're rapidly fixing that right now, which is great. Okay? But it's not great that it escaped their attention all this time. But on the other hand, it's great that it's going on.
Well, for here, there's always the issue of earthquakes.
Yeah, and here, of course, it's earthquakes. And I don't have to tell you, because everybody else in the room knows, I guess, that we're looking at that very carefully. And so is everybody, you know. That's right. But we're not worried about climate change per se, except as it might affect the frequency of these events, because that's not, you know.
I haven't got anything to say, but Dr. Lamb, you look like you're about ready to explode. What have you got to say?
Oh, no. You know,
He's allowed not to agree with me.
all right. I want to say for the record that Dr. Budnitz had gave a tremendous presentation on risk assessment as well as reactor safety. Now, since the chairman is absent, the committee still had quorum. We had Dr. Budnitz and myself.
Well, we're not taking any action,
Right.
though.
And before I adjourn the meeting for the evening, I would say, you know, Dr. Budnitz is certainly welcoming questions on this presentation. And I also would like to make it possible within the next several minutes for public comments.
Say anything you want for as
Right.
long as you want.
Right. Anything you would like to say about Dr. Budnitz's presentation, it doesn't have to be a question. You know, feel free to come to the podium and state it for the committee's record. So please identify yourself.
John Giesman on behalf of the Alliance for
Hi,
Nuclear
John.
Responsibility. My question is about the transferability of the frequency calculation between countries or between reactor
Boy,
designs.
oh boy, is that a good question.
Well, I kind of expected.
Let me say, of course, I can even jump right in. We have industry-wide data on most of this stuff that's robust, and we have plant-specific data on a lot of it too. But for some events, we don't have anything plant-specific. For example, there are some oddball failures for which the whole world database consists of 10 failures. And there might have been one in Spain and one in Argentina and two in the US and one in Canada and, you know, and two in Germany. And we have struggled, we the community have struggled with how applicable those data would be from one plant to the next, because plants are in fact different. They're different in culture, they're different in design, they're different in maintenance, they're different in vintage. And the general approach to that has been, for those places where the data are weak, to be very careful to assign uncertainty estimates to those that would encompass what we think is a reasonable range of high side might be worse, okay? But you always have the concern, you would be the first to say, I jumped in front of you. How do we know that the culture in country, I'm going to Armenia next week, how do I know that the Armenian plant, they don't have enough data there, so they've used worldwide data, and they have some they have. How do we know that their culture is such that those analyses are real for them? It's hard to know. It's not only a good question, it is a nagging problem, even from plant to plant. Just to give the example, no one would have transferred the PRA at Diablo to San Onofre. You got to do it there. There are just enough differences. Okay, and by the way, they're similar and culturally. You know,
Right.
Okay, so you bet that's a major uncertainty.
But when you have a diverse set of data inputs, let's look at the worldwide data set.
Yeah, it's diverse.
Do you end up weighting different elements of those inputs?
Yes, sir. The most important places where we see big differences are in the human errors. I'll just give you the example. It's easy to say. The Japanese, the Koreans, and in Taiwan have a very different human error rates than we have in our country. They're not very many, but they're lower. Some of them are lower, some of them are higher. It just has to do with their cultural differences, and those have to be accounted for sure. Okay? But in the end, none of us believe these numbers we come up with within a factor of 2. Anybody that says it's 3.2 times 10 minus 5 that you know that within a factor or two, that's baloney. We don't know them that well, but the numbers do provide a hierarchy, because something that's 3 times 10 minus 5 is a heck of a lot more important than something that's 3 times 10 minus 6. So because the numbers are uncertain, almost none of the numbers involved here are used in regulation. The NRC, correctly, doesn't use them in regulation. They use them to tell them what's important to look at in the regulations, and they have modified their regulations, okay?
It serves a ranking function irrespective of your level of confidence
Well,
in a specific
Yeah,
calculation.
but if you don't mind my saying, there's enough judgment that I'm in the community, it's what I do, that we go to international conferences and somebody will give a paper and another guy says, well, okay, but I just don't think that's as important as you do. And those are legitimate differences that you can't adjudicate. They're just differences. And the community has to sometimes deal with, there's 7 people and 2 of them think it's important, the rest of them don't. We better think it's important because, at least somebody does, even though I don't. So you have to, it's really complicated. There's more, despite all the engineering and all the analysis, there's one heck of a lot of judgment in trying to figure out what's what. And that's a piece of the management of a plant. And by the way, somebody like Ed Halpin, who's a PRA guy in his bones, by the way, he understands this. But it's also a lesson in humility, okay? We just got to be real careful not to get carried away,
Thanks.
okay?
Mr. Wiseman?
Yeah, David Weissman, Alliance for Nuclear Responsibilities. What you said at the beginning of that a bit about that, as Mr. Giesman had asked and you responded, well, it's hard to collect the data in some ways because the plants are all different. They're built at different specs, and that makes it difficult. And this is why I think using an airline industry analogy doesn't hold up as well.
It's fair. That's a fair comment.
Because there are about 3 models of 757s. There are 1,000 of them made. As I've said here before, they're in the air, if the airline is profitable, 20 hours, feeding
fair.
data in constantly, which is why the public's confidence, as you expressed, in wanting to travel on the plane is that high.
You're completely right. You're completely right. There's nothing like real experience.
And it's then to take that one step further, companies that also turn a profit, like AIG, Swiss Re, and other Lloyds and other insurers, knowing the statistics, as you said, have grown increasingly favorable for airline travel safety, are willing to underwrite that risk at what must be both a profit to the insurance company as well. But if in turn, then, as you point out, the probabilistic numbers look as good for the industry you speak on behalf of, and a profit were to be made by the insurers, yet they never have.
Oh, I'm not arguing that. I'm not arguing I'm speaking on behalf of anything. The fact is those numbers have validity despite the uncertainties, and different people make different judgments about them. I mean, you might judge and I might judge the acceptability of something as being unacceptable or quite acceptable, but that's different than speaking about what the numbers tell you. The fact that insurance companies behave in a certain way is a judgment they've made, okay?
And we'll just leave it at
No,
that for now.
I want to pursue it because it's not a small point. The fact is that the key to what we're trying to do is to understand this plant and to try to help figure out how to improve it where we can, okay? And to report on its problems to the public, as we do. We're trying here not to make a judgment about the overall acceptability. That's not our remit, okay? And insurance companies make a different judgment, and, obviously PG&E makes a different judgment, okay? I didn't want to go there, although I understand your point. It's not only a profound point, it's the key societal issue.
Because I make a decision whether I choose to get on the plane or not, but I can't make a decision whether, even if I choose to live 150 miles away, radiation from the improbable, unlikely, but inevitable, might happen in my direction.
I agree. I completely understand that. I mean, by the way, it's not completely analogous. The plane might land on you.
That is true. It is
I mean, but it's pretty, it's pretty small. But,
and I'm certain that I would. And I'm certain that I would.
I only made that because although it's quantitatively, it's nonsense. I don't spend my life worrying about a plane falling on me. But in a qualitative sense, we all make those judgments, right?
Though, if you think about the terrible accident that followed 9/11 in Brooklyn, of the American Airlines plane that went down in that Queens neighborhood.
Boy, I know.
Odd, but it is possible to have loss on
No, I
the
know.
ground.
I do know.
And I would suggest that you maybe take
It's pretty small, but it's not.
reinvestigate your interpretation of the causation of airline crashes, especially in the last decade and a half to 2 decades. Just my hypothesis, you would find it's about 50-50 on human error versus mechanical error, and sometimes the two are interlinked.
Well, yeah, they are, but actually, I don't think it's like 50-50, but go ahead.
Okay, I'm just thinking of these, you said the major crashes, we're talking about loss of lives.
Yeah, no, we're talking about crashes that kill a bunch of people. That's right.
At a time. I could, since to take the audience's time, name a dozen of the big ones and find out something failed. The pilot, not having the information they needed, then doesn't know how to respond to it. And likewise, the opposite can be true. Birds strike
That's
a
true.
plane,
That's fair. That's
and
fair.
Captain Hero Sully Sullivan manages to land that plane in spite of the odds that have said he
God
wouldn't
bless
have.
him,
So
right? Yeah.
it can go either way. Thanks very much.
Thank you. Thank you. I understand that distinction. It's really a hard one because there's so much interlinking of what the humans do and what the machine is doing. Yeah, go ahead. Right.
I plan to keep this really short. Don't need to discuss anything you said. I'm just accepting it all.
Please,
It's fine.
please, for
Hey,
our
can I
record,
say something? Can I say
please, for our
something?
record,
I love you too.
introduce, please.
Well, I didn't say that.
I know, but I did.
Miss Swanson, please, for our record, would you introduce yourself?
Thank you. I'm so sorry. Jane Swanson, spokesperson.
I hope you took that straight, okay?
I took it fine. Jane Swanson, spokesperson, San Luis Obispo Mothers for Peace. So, for the moment, what I'd like to do is take as given everything that Dr. Budnitz explained about PRA, which was very useful. Thank you for the education. And let's assume that the analysis that the industry is greatly reducing the risks of core failures because of their understanding here. Let's take those as given. I just want to make the statement that the position of Mothers for Peace doesn't argue with those facts, but we have an ethical position, which is that if everything goes well, no human error, no core releases, you've still got radioactive waste that's
Yes,
going to be
ma'am.
lethal for 1 million years, and therefore, in our view, the whole entire industry, not just Diablo, the whole entire industry is not justified on behalf of humankind.
Yeah, Jane Swanson, Jane Swanson, I'm not going to dispute what you said for a minute because I was talking about reactor safety.
I know. I love you too.
I mean, the fact is that we could have a whole session here about waste if you want, but that wasn't what I was talking about. I know, we know each other. Gerald Strickland.
Hi, Gerald Strickland with PG&E. I wanted to thank you for the discussion. The Probabilistic Risk Assessment Group reports to me at Diablo Canyon.
I know.
And in turn, it is a really valuable tool in that on a daily basis, we rerun that analysis that looks at what happens when we take a piece of equipment out of service. And in turn, then it helps provide insight for the plant for the maintenance cycle as to what aspects of the plant that you need to afford additional protection while we have a piece of equipment out of
Got
service.
to work like the dickens on this thing because it's really important to make it.
Well, and also we have redundant trains in the plant. And so if I've taken one train out of service to be able to do some maintenance, then I can look at what is the risk of having an incident on this other train and what components or other portions of safety-related equipment have an impact on that redundant train. So then I have a larger family of equipment that I then need to protect to be able to then effectively do the
And
maintenance.
Gerald, isn't it so? I know you'll say yes. Certain things you would used to do, you say, I don't want to do that until I've got this other thing here because it's too risky, and I didn't know that until I did this analysis.
Well, that's correct. And that's why you'll see certain types of maintenance that is scheduled for refueling outage and not scheduled for online maintenance. So the
Right.
probabilistic risk assessment tool gives you additional insight that you can do, that you can utilize to be able to improve plant safety.
Right. And I suppose you'll endorse entirely that this concentrated on accident sequences that I talked about is the key to understanding these equipment issues.
It is, and it's something that, as an industry, we continue to study and update the information that then feeds into this probabilistic risk assessment set of tools. As part of the recent orders from the Nuclear Regulatory Commission, we're in the process now of updating our seismic probabilistic risk assessment as well as our fire risk assessment. And again, that will provide us even better tools going forward.
And now I'm going to put a bug in your ear that you know about. I chair a committee, an ASME A&S committee that produces the PRA standards. I mean, there's 35 of them. I co-chair it. And we have just issued a standard for PRA during shutdown. But it's not ready for use yet. It's still in a trial. But I know, because I've talked to your colleagues, that when it's ready in another year or so, you're going to go look carefully at doing that too.
That's correct.
Right. But it's still to come. Turns out that when the plant's shut down, it's not of zero risk. There are risks when it's shut down.
That's correct.
Sure,
Thank
as
you.
as long as you're up there, if I could ask a question
Sure.
to the two of you. And I've been away from this for quite a while. To what degree, when you talk about the importance of control room operators, to what degree now are procedures, emergency procedures used by the control operators oriented toward responding to symptoms, basically being symptom-based, as opposed to requiring the operator to diagnose exactly what's going on and then acting
He can
as
answer
a
that.
result of, and having the thing being event-based, that he has to diagnose what the event, and he could be wrong, as opposed to being assisted by just being able to respond to symptoms.
It's tied to symptoms in that
It is.
we have a programmatic set of procedures that then take you to where if this is the case, then proceed down this path. And so it gives you a very definitive path to follow to be able to then ascertain appropriate next steps.
Right. Yeah, just along that line, because when the bells and whistles are going off, it's sometimes easy to get mixed up as to what what event is really going on. But it's much more clearer. It's much more clear if you have just be able to understand what the symptoms are.
And we'll talk more tomorrow morning when we talk about flex equipment, but that's part of the process that's being put in place for flex responses is to have all these various integrated procedures and programs to be able to then give the operating team the correct path to be able to implement the flex procedures and processes for beyond design-based events. Okay. Thank you.
But some of that is a work in progress as follows. The sort of flex equipment that's installed in the plant, we understand. But some of flex equipment's going to be in a shed somewhere and they have to bring it in. And we don't yet, the community doesn't yet understand whether the probability of success in bringing it from the shed and plugging it in is 99 out of 100 or 999 out of 1,000 or it's a 5% chance of failure. We don't know that yet because there's not enough experience. So if you want to do a PRA to understand the probability that that portable equipment isn't going to actually get plugged in and work, we don't have enough experience to do that yet. So the PRAs that are being done on that, they're doing them, but there's still some uncertainty, and it's going to be a while before we have, everybody's going to do this a few times and test it and find out where the errors are, and somebody made a mistake, and then they're going to fix it. So until that's gathered, we're not going to know enough about that in a probabilistic sense.
Right. Now, before I adjourn the evening meeting, let me close by saying this very useful dialogue may continue after this meeting because Dr. Budnitz is always available to talk about it. And also to those participants in this proceeding who may not be proponent of nuclear technology, even if you are not persuaded by Dr. Budnitz's arguments, you should be impressed by his passionate delivery and very enthusiastic presentation.
I'm only an analyst, is all I am.
Right. That said, let me adjourn this proceeding for the evening and remind everybody